Swayam Prabha. Digital India. Educated India.
In this lecture, let us revisit the concept of waves. We would like to have a look at the conservation equations once more, both inviscid and viscous flow conservation equations involving compressible flows and shocks. When we revisit waves, we would like to look at the theory as well as the numerical solutions. Governing equations, the conservation equations for viscous and inviscid compressible flow, namely the Navier-Stokes and the Euler equations. And we would also like to look at thermodynamic properties across normal shocks, the effect of degree of freedom of the gas, the concept which we will discuss briefly and explain what is the impact of that on the thermodynamic properties. So, we once again come back to this question, what do we mean by a wave? And as you may recall, we had talked about this definition that wave motion is defined as transport of energy and momentum from one point to another point without transporting the matter. And we have cited two equations over here, as you can see. So, one is a linear wave equation, the other is a nonlinear one. And we will also try to explain how the solution of these two equations look like. To begin with, the linear wave equation, where you have del u del t plus a times del u del x equal to 0. This advection term is a linear term because of the coefficient associated with the del u del x term, which happens to be a constant. It is essentially the wave speed that we talk about, and when that becomes equal to u, then it turns into a nonlinear equation, 1D nonlinear advection equation, and that one change brings about a very dramatic change in the behavior of the governing equations. So, we will see soon that how that impacts the solution. So, we would first like to look at the solution from an analytical angle, that of the linear advection equation. So, the first order form of that defined over the spatial domain minus infinity to plus infinity, the variation of x, and with initial condition u x comma 0, that means at t equal to 0 is equal to u naught x. So, that is some kind of an initial distribution of the dependent variable u, and then the solution will be u equal to u naught x minus a t, where x minus a t is going to be the wave front as a function of time, and therefore, basically what would happen is that this waveform that you have defined through the initial condition over here, it would just get translated at the velocity a as time progresses. So, the a times t is basically the displacement that the waveform goes through, but there is no change in the shape of the waveform as such. It does not attenuate, it does not distort, and so on. The second order form of the same equation over the spatial domain minus infinity less than x less than infinity would be of this form, u equal to u 1 x minus a t plus u 2 x plus a t, where x minus a t and x plus a t again are the wave fronts propagating in the two directions. So, this is a form which you saw over here. This propagates to the positive x direction, while the other form propagates towards the negative x direction. So, this is the analytical solution of the linear wave equation in the first order and second order form. If you look at numerical solution, let us say of the first order form, you can write a simple Python program like we have shown over here, or you can write it in other languages, whichever you are aware of, whichever you know. It could be C, C++, Fortran, any of those languages would be good enough to write such programs. And here, if you look at the structure of the program, we have just shown a few lines of the program. The NT is the number of time steps over which we would like to march the solution, and therefore, the wave would progress over time. And it starts with an if statement where A is greater than 0. That means you have a wave moving towards the positive x direction, and then n is the number of grid points that you have considered in the domain. And for that entire range of grid points that you have from 1 to n, you are trying to carry on this calculation by discretizing this governing partial differential equation with an algebraic equation. I had briefly mentioned about this in an earlier lecture, that how to discretize a linear advection equation using upwind scheme. So, an upwind discretization has been applied over here. We had also talked about the CFL number, because that has to do with the numerical stability of the solution. And then the n over here basically indicates the time step at which you are performing the calculation, and the I is basically the spatial location. So, that is basically the grid location. So, you can imagine that there is some kind of a spatial grid like this spanning the entire length of the domain along the x direction. And if you look at a particular grid point, that has an index I, and the computation currently is going on at a time step n. You would like to progress it to the next time step n plus 1. As you apply this algorithm, the solution will move to the next time step n plus 1 at the same grid point I. So, that is the logic behind this. And then there is an else over here. That means if you are not having a greater than 0, there is an alternative logic that you have to apply over here. So, I leave it as a little bit of a homework for you to figure out how this would be working. And if you apply such a program, the solution will emerge like this. So, you have the initial waveform defined, as you may recall that we had talked about a functional distribution u naught at t equal to 0. So, that is the wave description at the initial time. At some point of time you have defined it, and then you have progressed it over time. So, it is already 0.05 time steps ahead of the initial condition, and it has actually started advecting along the positive x direction. So, gradually as the time progresses, you will see that the wave moves towards the right. So, initially it was the center of the wave was somewhere over here, and as you reach t equal to unit time, it has already moved to a very different location, depending on what wave speed you have defined for the problem. What you see over here is an unattenuated advection of the initial waveform. So, attenuation in the sense the amplitude of the wave, because it remains at unity. So, in numerical schemes we may have some errors which may reduce the amplitude of the wave as the solution progresses. That is called as a dissipation error, but that is not seen significantly over here. There is practically no dissipation error. If there is any kind of distortion of the waveform, that is called as a dispersion error. So, there is no distortion in the waveform also, no noticeable distortion of the waveform that you can see over here. That means it moves unattenuated and undistorted. So, this is going to give you some more insight into propagation of a waveform following the linear advection equation. Now, if you look at the solution of the nonlinear advection problem, as you may recall that this term u, introduction of this term u in place of a, which was a constant, this is now a variable and it can vary from one spatial location to another and from one time step to another. So, here you see again that the spatial domain spans from negative infinity to positive infinity, and you are going to march it over n t number of time steps, and you are going to discretize this equation and implement the solution over here for a greater than 0, or otherwise you have two sets of statements defined over here, and how you are going to update the solution from the nth time step to the n plus 1th time step. So, again a few lines of Python program which should help you understand how the solution progresses over time. Now, if you look at the nature of the solution, it is now dramatically different. So, it begins with a waveform very similar to what you had for the linear program, so for the linear problem, I am sorry, and then as it progresses, you see that there is some kind of a tilt coming in the waveform, and then it starts getting steeper at this end, and by the time it reaches unit time, it is indeed very steep, looking more like a shock, a sharp change, which basically means that in this waveform not all the different sections of the wave are propagating at the same velocity, but rather at different velocities, and it seems that the later part of the wave is catching up with the earlier part of the wave. So, the front and the rear, if we call it that way, the characteristics which are associated with the front and rear portions of the waves, they are not moving with the same velocity, and that is ought to be, because earlier they were moving with the same velocity a when it was the linear advection equation, but now it is going to move with u, and u being a function of x and t changes from time to time. Essentially what is happening over here is that the u is from a very low value over here, goes to a large value here, and then again drops down to a low value over here, which means the characteristics at these locations, in these locations, are traveling much faster than the characteristics in these locations. And the concern is that when these faster characteristics catch up with the slower characteristics here, there is going to be a formation of a shock like this, because as you may recall that in the characteristic space, if you had a x by t plot, this is how you would see them moving, and therefore, they tend to converge into one strong front, and that is what is seen over here. So, through this solution you get more insight into how the wave is really behaving as it advects. So, we had a brief discussion once again about waves to give you some more insight, and now it is time to relook at our governing equations. So, this is the Navier-Stokes equation, the viscous compressible flow equations. We recall that we were talking about three main conservation equations. One was the continuity equation, the other was momentum equation, and the last one the energy equation. And here we have written them in integral form. That means, we are talking about the control volume approach, and we are also using the Eulerian approach. So, we are fixing our location at which we are viewing the flow. We are not following a fluid element or a control volume, and we have also indicated the equations in the index form. So, I hope you are now getting more familiar with the index form, and you are also comfortable with the rules and guidelines in handling the index form. We have marked the different flux terms varying from A to J. So, you should be able to recall the interpretation of the different fluxes A and B referring to the fluxes involving the continuity equation, the net rate of change of mass and the net mass efflux through the control surface, which gives you the effects in the continuity equation. There are 4 flux terms in the momentum equation: net rate of momentum change inside control volume, net momentum efflux through the control surface, net surface force and net body force. Not that every term will be applicable for a given problem, but we have put them in a more general form over here. And coming to the last equation, the energy equation, again you have 4 fluxes: net rate of energy change inside control volume, net energy efflux through the control surface, work done by surface forces, work done by body force and heat transfer. So, this is the most general framework, and as you may recall, when we define the sigma ij term, which figures in the momentum equation as well as the energy equation, this is the most general form involving the effect of pressure, the viscous stresses and the bulk modulus. And if you look at the viscous stresses, again for a Newtonian fluid, you will only have this portion with an index of 1, and the E term in the energy equation of course involves internal energy and the kinetic energy part. So, you should be able to recall these equations at any point of time as we move along the different lectures of the course. If you look at the inviscid governing equation, the Euler equations, that means we have no viscous stresses, then the equations get simplified, and then you may recall that from the continuity equation, when we had specialized these conservation equations to handle a normal shock, then we got to simplify the continuity equation to a form like this, assuming that the flow was steady, and then we defined the 2 states 1 and 2, one ahead of the shock, the other behind the shock. So, this is basically the shock front, and we have also indicated it with the blue and the red colors respectively, just to distinguish. When it comes to the momentum equation, the inviscid form, we have only the pressure acting from the sigma ij term, there are no body forces, and again if we neglect the unsteady term, we would only have these 2 terms contributing, and then when you integrate it over the control volume which envelops the normal shock, you are able to get this governing equation where P plus rho u square is conserved across the normal shock. Coming to the energy equation, we assume again that it is steady. We also assume that there are no body force effects and heat transfer effects. So, we assume it to be an adiabatic flow, and then these are again the only terms which are contributing. Of course, we continue to assume that it is inviscid. There are no viscous stresses because we are handling the Euler equations, and therefore, the energy equation boils down to this, which can also be written as this in terms of the enthalpy, and which means that the stagnation enthalpy is conserved across the normal shock. So, these are indeed very important forms of equations that we should always recall when we move along the course. Now, coming to the thermodynamic properties across a normal shock wave, you remember that gamma is a very important term in compressible flows, which is basically the ratio of specific heats Cp by Cv, and gamma can in general be represented in a form like this: gamma is equal to 1 plus 2 by n, where n happens to be the degrees of freedom that is available in a given gas. If we increase the temperature of the gas from top to bottom, then we see at much lower temperatures only the translation motion of the gas molecules are active, and at those lower temperatures the gas indeed behaves like a calorically perfect one, where Cp, Cv are all constants. Then the rotational motion sets in. We still continue to have that behavior, but then with rise in temperature it becomes thermally perfect gas, where the vibrational motion sets in, and then the Cp, Cv start varying and they depend on the temperature of the gas. At still higher temperatures, generally of the order of few thousand kelvins, the electronic energy modes also get excited. So, these are the different energy modes which are gradually getting excited with rise in temperature, and then we start seeing the real gas effects. As the temperature rises, the degrees of freedom of the gas vary, and consequently the gamma varies according to a form like this. Just to elaborate on that concept a little further, at very low temperatures close to 0 Kelvin, only translational energy mode is excited. And if you look at the diatomic molecules, which is of interest to us because air is mainly constituted of diatomic molecules, namely nitrogen and oxygen, the Cv of the gas is found to be 3/2 R. We can prove these values or expressions if we go to the microscopic thermodynamics. We cannot do it from the classical thermodynamics point of view. We will do it slightly later in the course. Cp would then be given as Cv plus R, and then it will turn out to be 5/2 R. When it comes to gamma, the ratio, it will be given by 5/3, which can again be expressed as 1 plus 2 by n form, where n becomes equal to 3. That means, at very low temperatures n would be 3. At moderate temperatures of about 600 Kelvin or so, both translational and rotational modes of energy are excited. Hence, for diatomic molecules, it can be shown at those temperatures based on the excitation that Cv will turn out to be 5/2 R. Cp again with the addition of R over here with Cv gives you 7/2 R. The gamma ratio gives you 7/5, which can be expressed in this form, where n comes out to be 5. It is to be noted that for the atoms which exist at these temperatures, Cv is not 5/2 R, but rather it is 3/2 R, because there are no rotational modes which could be excited in single atoms, and therefore, the Cv varies depending on the kind of medium that you are handling, whether it is monoatomic or diatomic or polyatomic. When vibrational, rotational and translational energy modes are all fully excited, which is at a much higher temperature, say around 2000 Kelvin or so, we can show that Cv becomes 7/2 R. Consequently, Cp becomes 9/2 R. Gamma, the ratio gives you 9/7, and therefore, n becomes 7. Now, obviously, this means that n would vary as the temperature varies, because of the excitation of the different energy modes within the gas. And consequently, what would happen is that you would have a range of gammas, which you will see as the n varies. Now, as a consequence, you will find that the thermodynamic properties across the normal shock wave would change as the n varies. So, if you were to use the P2/P1 form, assuming the gamma to be constant, for air we assume it to be 1.4, then P2/P1 as a function of m1 varies like this. So, at m1 equal to 10, you see that P2/P1 takes up a value beyond 100. Now, if you were to plot it as a function of the number of degrees of freedom, here you can see that they are varying from 1 to 7. This axis shows the Mach number, the other axis shows the pressure ratio. Then the pressure ratio takes a certain profile, it has a certain envelope which has slight variation from what you see over here. It gives you a 3-dimensional surface as a function of the degrees of freedom. If you were to see the density ratio, you will see that we know that for gamma equal to 1.4, in an earlier lecture we had shown that rho 2 by rho 1 would tend to a value of 6 as m1 tends to infinity. So, that is the kind of trend that you are seeing over here. while you will see, if you look at this end of the plot for the different values of n, then you will see that it is saturating at a different value closer to 7 or slightly beyond. That means there is an effect of the number of degrees of freedom over here. So, there are some more plots which we would like to discuss and a little program as well, but we are running short of time in this lecture. So, in this lecture we discussed about linear and nonlinear wave theory and saw some numerical solutions to appreciate their behavior. We revisited the governing conservation equations for viscous and inviscid compressible flow. We saw the effect of degree of freedom of the gas on the thermodynamic properties across normal shock. The results were generated using a Python program, which we will try to discuss in the next lecture. Thank you.